My name is Eric Fulmer. I'm here for Team Bike Philly, and today I'll be talking to you about our project, Philly Bike Share, which is a bicycle sharing program. Bicycle sharing program is basically makes bicycles available for short-term rental. Quick team overview. Like I said, I'm Eric Fulmer. I'm team leader and electrical designer. John Waldron will be in charge of the bike rack design. Steve Pham will do the lock design, and Mark Transu will do traffic modeling and will assist in the structural design of the bicycle rack. Our advisor is Dr. Miller, and our coordinator is Dr. Cohen. In 2012, Mayor Michael Lutter of Philadelphia requested funds for the implementation of a bicycle sharing rack in Philadelphia. So our goal as Team Bike Philly is to design a user interface along with a bicycle rack with locking mechanisms and bicycle to be used in the bicycle sharing program. Why do this? Well, travel expenses are constantly going up with the fuel prices increasing. Public transportation becomes more and more crowded every day with the increase in population. People rarely get time to exercise these days, and the environment is constantly depleting. So our program will help to solve some of these problems. Like I said, our primary task is to design a user interface, bicycle rack, and bicycle for a bicycle sharing program. We will focus on ease of use for the customer, and we will attempt to eliminate theft and vandalism as much as possible. We hope to encourage a green and healthy mode of transportation and help to decrease the congestion on the public transportations like buses and trains. We hope to provide bicycles to people who do not have a bicycle, and it will be limited responsibility for them, and they will not be required to do any kind of maintenance. Functional constraints. The locking mechanism, we hope to have the locking mechanisms to perform their locking and unlocking functions in less than 3 seconds, and we want their life to be over 73,000 cycles, which equates to about 10 years of use. Lock and bicycle security. We will design the bicycle rack and bicycle lock so that it will withstand the force created by a 300-pound force on the handles of 2-foot-long bolt cutters, as well as the force created by a 2-foot-long crowbar. The strength of the rack itself, we will design it so that it will withstand a load capacity on top of 500 pounds. This will simulate a person sitting on it or the collection of snow or ice. The bicycle design, we want to choose the simplest design possible, so what we will use is a fixed speed bicycle. I'll go over that a little bit later. And we will modify the bicycle so that it is as theft-proof as possible. Non-functional constraints. Cost is a major factor. We want to keep the cost as low as possible so that the cost to use our program is low, which will encourage customers to use our mode of transportation rather than using a taxi or bus. We will design the rack and the locking mechanisms to be as durable as possible to make maintenance as infrequent as possible and to lower the maintenance cost. The design of the rack will be made simple so that they can be mass produced, because we'd like to place several of these all over the city. Major challenges and risks. The two largest challenges in a bicycle sharing program is deterring vandalism and deterring theft, because if we do not do this, then the success of this program will be in major question. The location of the bicycle racks will have to conform to all the Philadelphia zoning regulations. Competition from other forms of transportation, like I had mentioned, we need to keep the costs down so that people will be encouraged to use our rented bicycles rather than go out and buy their own. Here is our design block diagram. As you can see up top, first we need to determine the exact design of the bicycle that we will use. Once we've done that, we can begin to determine locations around the city where we can place these bicycle racks. We can then finalize the design of the bicycle locks, the user interface, and the bicycle rack. Once we finalize that, we can begin testing these components individually, and then depending on how the test goes, then we can then put it together and build a prototype, and then begin to test our prototype. This is just a quick overview of how the program will work. Customer will approach the bicycle sharing station, has the option to use a credit card or an RFID scanner for more frequent users. The bicycle will unlock from the bicycle rack. Once the bicycle is returned and locked in the rack, the customer will be charged for the duration of their rental. If the bicycle is not returned within a 24-hour period, then the customer will be charged the full price of the bicycle to ensure that they bring the bicycle back. It's a quick visual of how the user interface will work. The brain of our user interface will be the M91 PLC. It will communicate with the credit card reader and the RFID reader, and will provide the signal to the locking mechanism to either lock or unlock the bicycle. Security of the bicycle. We will do our best to secure all the components to the bicycle to prevent anyone from tampering with them, such as the front, the rear wheel, the seat, handlebars. Those will all be locked on tight. The seat will be adjustable to conform to users of all heights. You can see up in the corner the SolidWorks drawing of how we will do that with the seat. It will not be removable, it will be adjustable. Like I mentioned earlier, we will use a fixed speed bicycle. Why are we going to do that? Well, like I said, it's very simple, and it completely gets rid of the potential of gear issues that we may have in the future. Also, the nice thing about the simplicity is any user, young, old, or of any bicycle riding experience will be able to handle our bicycles. Here is a drawing of the rack design. The rack will be constructed of 1.5 inch by 1.5 inch by 1/4 inch thick steel angle iron. We chose this material because it's very strong, very sturdy, and will last a long time. The frame will be 37.5 inches tall and about 5 feet long, and will be enclosed in sheet metal panels to secure all the components within. Here is a SolidWorks drawing of the complete assembly. As you can see, the front wheel of the bicycle is concealed within the rack so that people cannot tamper with it. The sheet metal paneling has been applied to the outside surfaces of the rack. If you look at the other side of the bicycle rack, we've added 2 access doors so that the front and the rear locking mechanisms can be accessed quickly for maintenance. In addition, that allows us to conceal all the fasteners that will hold the sheet metal panels on so that people can't take the panels off. Only we will be the ones allowed into the bicycle rack. Here we've done a simulation on the bicycle rack. We placed a 500-pound load on top, and the bicycle rack has held up. Here's a cutaway view of the assembly. The front lock will be located slightly above the front tire. The rear lock will be located slightly above the rear tire. And the user interface will be placed on top of the rack above the front tire. We've chosen this place because it's on the bicycle rack, so we don't have to have a separate station, and it's at a reasonable use for all people, tall and short, to use. The front lock. The front lock will be a solenoid-powered deadbolt style lock. The deadbolt will slide across through the hole on the plate mounted to the front of the bicycle, thus securing the bicycle into the rack. And once the signal is given to the spring-loaded solenoid, the deadbolt will retract and will allow the bicycle to come free. We've done a SolidWorks simulation on the front lock mount as well. We placed a 300-pound load on the deadbolt to simulate a person applying 300 pounds on the bicycle, trying to remove it from the rack, and the rack has, or the mount has held up. Here is the solenoid that we have chosen to use. It is powered by a 24-volt DC signal, which is compatible with our PLC. It has a 1-inch stroke, which we chose the longer stroke so that we could use a thicker plate on the front of the bicycle to allow for higher security. Like I mentioned earlier, the life of the locks will be 73,000 cycles. That's 365 days in a year, times 10 years, times 10 uses a day, 2 times 2 to account for the locking and the unlocking of the bicycle. Here's the rear lock. The rear lock features a rotating arm that will rotate out and hook the bicycle to secure it to the rack. This will prevent anyone from trying to lift the bicycle from the rear tire or swing it away from the rack. The rotating arm is powered by a low-speed synchronized stepper motor. Once the arm has rotated into the locked position, a pin attached to a spring-loaded solenoid will engage, locking the arm into that locking position. Once the unlock signal has been given, the solenoid will retract the pin and the arm will be able to move to the unlock position. We found a weak point in our the rear lock assembly. At this point, we calculated the resultant force of someone using a 2-foot crowbar to try to pry the L-shaped arm back and release the bicycle. That force came out to be a little over 4,000 pounds, so we ran a SolidWorks simulation. The brain of our user interface will be a programmable logic controller, or PLC. The reason that we chose this PLC was because it already has a screen and a keypad on it, so we don't need to worry about attaching those. And this will provide us with our locking and unlocking processes. Here we have our radio frequency identification, or RFID, and credit card swipe. This is how the customer will pay for their rental. Cost analysis sheet, we broke down the bicycle rack into its components. We have the metal stock that the frame will be built of. We have the sheet metal panels, the hardware, and then the electronic components. And all that together comes to slightly under $800. Traffic modeling. The traffic modeling will be done on existing bike paths and major city streets. The program that will be used is called Visum. The traffic modeling will show the effect of having an increased amount of bicycles on city streets. The traffic data. Pedestrian, vehicle, and bicycle counts will be taken in certain areas around the city. These counts will be taken at peak hours from 7 to 9 a.m. and 4 to 6 p.m. Here is an example of just one day of traffic counts. Locations. Our program will run as far north as Temple Hospital, south to the sports complex, east to Penn's Landing, and west to University City. We will focus on placing these racks in key locations around universities and hospitals because of the higher population. GIS mapping software will be used to help make a better selection for where we should place these bicycle racks. Certain parameters will be used to help us find the ideal locations around the city. Parameters include population, age, bike lanes, etc. All the locations of these bicycle racks have to conform with the regulations set by the Philadelphia Complete Streets Design Handbook. These regulations include distances from like taxi loading areas, tree pits, bus stops, etc. Right here we have a map. These black bars you can see here, those are possible locations where bicycle racks can be placed. Summary. For the remainder of Senior Design 1, we would like to make a trip to either New York City or Washington, D.C. so we can get a first-hand look on existing bicycle sharing programs to help us manufacture ours. We'd like to finalize the design of the bicycle locks, the rack, and bicycle itself, begin designing the test, and start ordering components. That way, in the summer of 2013, we can build our prototype, which leaves testing for Senior Design 2 and any necessary modifications that may have to be made. This is our project schedule, like I said. Remainder of Senior Design 1, complete research and design. Summer, build prototype. Senior Design 2, run testing and simulations. So our references, any questions?
Any questions?
Have you looked up at luggage carts in the airport? They use basically credit card swipe, right? You swipe, you can get.
You said the carts?
Yeah.
Oh, the luggage carts. Oh, they use a credit card swipe?
Yeah, same ideas. Have you looked up the design?
No, actually, we haven't thought of that. That's something we will look into.
Yeah, I think it's what you do will be very similar.
Yeah, that's a good
Yeah,
idea.
actually, just I have a couple questions for you. You go back to your original, say, 500 pounds load.
Right.
Where do you come up with 500 pounds load?
Well, we just assumed they'll be located in popular city streets, so I'm assuming that people will be sitting on them. So we just accounted 2 people sitting on a bicycle rack, roughly 500 pounds. Now, we did run simulations for, I believe we went up to 3 tons on this bicycle rack, and there was some displacement, but for the most part, the rack stayed completely fine.
So when you did your analysis, you assume 500 pounds is evenly distributed?
Yes, for the SolidWorks analysis, yes, that's a distributed load.
You know, it's totally different when you have 500 pounds in the local load concentration versus 500 pounds, you know, spread out.
Spread out, right. Okay, yeah, that's something we will look into, doing a concentrated load of 500 pounds rather than a distributed load.
Any more questions? I am assuming that every bike will be identified as an RFID code. Is that what it is?
That's still something we're looking into. We're not sure how we're going to tackle that yet. We will need something to identify who's returning the bicycle. Like I said, I don't have a real good answer for you right now. It's something we're going to have to consider.
Okay, but suppose that someone takes a bike from one bag and put it on the other bag. It should be.
There will be interconnected,
Okay.
the systems, yeah.
How about the electronic payment, basically card swipe and that's what
That's what we will do for the purpose of our project. We're not really going to focus on that. We're going to focus on the rack design and the locks, and the RFID scanner and the credit card will simply be a simulation of how it will work.
So it will not be implemented?
Yeah, it will not be implemented. Yeah, the payment process will not be.
Because also like in the case of fraud, like somebody steals a credit card and goes and swipes and take a bite and wires it, so that there should be some checking there.
Right.
Okay, in the gas stations they tell you enter the postal code.
Oh, right.
So basically you can add something. Okay, thanks. Go
I
ahead.
have 2 questions for you.
Yes.
How do you know when you have a bike return, right? And how do you know the return is the same bike?
Well, that was one thing I was saying to him. We're going to have to look into that for so that our system will identify each bike. So if a bike's taken from Temple Hospital and returned to the sports complex, we'll have to design our system so that it will know that that's the bike being returned and to charge that person.
It's different. Well, I'm curious if you can use different bikes to return, right? It's pretty.
Say that again?
You can come up with different bikes and just return.
Unless you put an RFID, right?
Right, and then it would know exactly what bike it is.
Yeah.
Are you saying like a personal bike, you mean?
Yes.
There's the way the front locks, it's unique so that only our bikes will fit into it.
Yeah, that's the way to do it. Actually, I'm really confused by your solenoid, control your arm and also pin.
For the rear lock?
Yeah, you have one solenoid to control both pin and the arm. Yes, over here.
Yeah. Down bottom, there is a motor that will provide the rotation, and the solenoid will be spring-loaded to its natural position will be extended. So once the arm turns to the locked position, there's a notch cut out in the arm, and then that will prevent the arm from being turned backwards. Once the solenoid is powered, that pin will be retracted and will allow the arm to
So
turn.
you have solenoid and the motor,
Right.
separate motor.
Right.
I apologize, we have